we have stopped here, and let's talk about this one. What this means. Gentlemen, here, let's say here are permanent magnets. Let's say permanent magnet. And then here are magnetic field lines coming from here. First of all, let me ask you a question. Which one is correct? The first one, magnetic field line coming here, goes to here. That is the first one. And the second one, magnetic field line comes here and goes like here. Which one is true? First choice or second choice? Please write it down in the chat box. First one or second one? Which one is true? I'm waiting a response. Which one is true in your opinion? Okay, let me explain one more time. Here's M pole, here's S pole in the stator, and of course here is yoke behind the poles, you know, and then magnetic field lines will come up from M pole, passes through air gap, enters the rotor core, passes through air gap, completes its circle. And now, here in the pole tip, here is the pole tip. Let me change color. Pole tip. In the pole tip, I offer you two solutions. One is the green line. Magnetic field lines come up and passes through the first path. This one, is it? Or the second one? Destina says the first one. What about Mohammed? No idea. Okay, let me remember you. Remember you here in the an empty blank page. Remember electromagnetic field theory last year. There were, let's say, positive charges, and then here were equipotential lines, and magnetic electrical field lines were always perpendicular to equipotential lines. E field, that is the voltage, E field was always perpendicular to equipotential lines, that is the potential. Okay, the similar action can be defined for magnetic field. Let's say here is an EMF lines. Here it is in the pole, and then here is the rotor. What is the current path? Remember, current flux path, flux path always leaves the medium in a right angle. They are always perpendicular to EMF lines. Here it is perpendicular, and then again here it is perpendicular. So magnetic field lines will be like this. Okay, the second choice was the correct answer. Here the second choice is the correct answer. Okay, let me complete the field lines. Here's the equipotential lines. And you know, magnetic field lines always prefer the shortest path. The shortest path. And then it would be like this, and like this. And here again, some of the lines will be like this. Magnetic field lines will be like this. The shortest path will be chosen for the magnetic field lines. Okay, let me search for magnetic field lines. Magnetic field lines around poles DC, let's say motor. Images. It's not clear. It's not clear. Something better, but not clear. Okay, let me make it more precise. Some analysis. Okay, DC motor. There are lots of different machine types examined here, but there is no DC machine. FEM DC motor, or let me say PMDC perhaps. It is more recent machine. It is not very clear, but you can imagine. Here are the flux lines, just a representation. Flux lines prefer the shortest path. There are two clues. They are always perpendicular to equipotential lines. Equipotential lines. So they are always enter vertically. Leaves vertically, enters vertically. Let me show you again. For example, here's a leakage flux. Leakage flux. Leaves perpendicular and then enters perpendicular. That is the general approach. You can easily estimate. We assume that here's an equipotential line. Here's the equipotential line. EMF line will be like this. Here it would be like this. It depends in fact, EMF line. If there's a equal potential in MMF, the flux waves will be perpendicular. Here it will be perpendicular and enters perpendicular and chooses the shortest path, not this one. it chooses the shortest path. Okay? And then, what Mustafa means? What does Mustafa mean? Mustafa means that if you start here, let's say 0 point, and then move along positive theta, that is theta, move along positive theta. First you come to the midpoint of N, here it is, and then here, you are here right now, and then in the middle of S, you are here right now, and then starting point, you are here. And as you see, it is cyclic. It is cyclic. And then, what is the function of B while you were strolling around the stator periphery? You start here and you make strolling, walking around, and then you face with such a B distribution. Fluxes, here are some flux lines, yes, but they are rare, very small amount of magnetic fluxes here. But here it gets dense, more dense. Excuse me, dense, more dense, because more flux over cross-section area makes more flux density. So flux density about from here to here almost will be constant, you see. It is a design. We made this on purpose. We made a special design on pole faces. Let me show you pole tips. Pole face DC motor. Pole face DC motor. Pole face. Here you see a special pole face. Let me show you. Here's a special pole face. And under the pole face, almost B flux density almost is constant. But here it is 0, but here are only leakage fluxes causing very small amount of flux density. Let me show you. Here it is. These portions here are leakage fluxes, some leakage type, because the main path is here, that is the main path, but those are here are very small amount of fluxes, so cause a little flux density. That is the B of theta. B flux density distribution around the stator or around the air gap. Air gap is better, in fact. Air gap B distribution. Okay. Now, ladies and gentlemen, I have just walked around the rotor as a Mustafa. Mustafa started here, come to the midpoint of N, and then come to here, which is, that is the pole axis, you know. Let me write it down. That is the pole axis, D axis, pole axis, magnetic axis, and then that is the axis which is perpendicular to D axis. It is called as Q axis or quadrature. axis. Sometimes we say magnetic axis. This guy, magnetic axis. You see, and that is sometimes called as magnetically neutral axis, because here is no magnetic pole. You are here in the 0 point. There is no magnetic pole. So what will happen? Please take care. I install a conductor here, and then I move the conductor. Let me write first. I move. Here's, excuse me. I'm applying left hand 3-finger rule. The magnetic flux, and then current will be entering. Okay, it doesn't matter. Okay, let's assume that this conductor here, here's another, moves in such a direction, and then apply left hand 3-finger rule. Let me switch on my camera. I hope it is available. Okay. Yes. Please first look at the figure. Mid finger from left to right, and then that is the thumb in moving direction of the conductor. That is the moving direction of the conductor in my camera. That is the magnetic field density from N to S. And you will find out the induced current's direction with your index finger. That is the index finger. Into the page, into the screen. Okay, I show here cross. And here is, it is opposite due to opposite magnetic poles. In fact, you can apply, it will be different, but magnetic field N to S, okay. The moving direction of the conductor is like this. Okay, apply it. Magnetic field lines is N to S. The moving direction of the conductor is like this. And then current is up to you, out of the screen. Okay, that's it. Now, let me switch off camera. Now, ladies and gentlemen, if you induce such a current, that means here is something to have such a current. Here, you should induce such a polarity. Just compare the current direction with a simple battery. Here's the battery. Make a comparison. To have such a current, you should induce plus and minus polarity. So here it is inversed, reversed. So you got a larger EMF. Perhaps it is given in different direction. It doesn't matter. What you see is important. Now, ladies and gentlemen, let me summarize what I mean. Here are magnetic field distribution around the air gap, and I install some conductors in rotor here, and then when I move conductors, there will be some electromotive force induced due to Faraday's law, or speed EMF. We call speed EMF. E equals to BLV. There is B, which is B of theta. It is B of theta, you see. And then there's a length of conductor. You observe here, there's a length of conductor. There's a length of conductor. Okay. And then we have moved the rotor. Yes, there is. So induced electromotive force, ladies and gentlemen, will be function of theta. Theta. The function will copy itself to here. Ladies and gentlemen, that was B of theta. And here you see E of theta. E of theta. The distribution will affect the EMF function. Yes. Ladies and gentlemen, in the previous course, we have studied on the operating principle of generator or motor and the commutator mechanism. The commutator mechanism was rectifying electromotive force mechanically by making commutation. So here, let's say here is a commutator. Here are two segments. There are some brushes touching. Here you see two brushes. And then there is a commutation. As a result of commutation, this side will be rectified up to here. This side will be rectified up to here. Almost each side, in fact. That is the voltage induced across the brushes. Let's say E1 and 2. Rectified voltage is this. Rectified voltage. It looks like not a sinusoid, not a square wave, something between them. Yes. Okay, what does it mean? For example, in the given example, here were only one coil. One coil result in such a E theta. There were two commutations. For example, let me show you. Oh, it is difficult to imagine. First, the brush B1 is connected to coil side A via brush and commutator segment mechanism. Here it is connected to here. Then, when you move rotor in any direction, let's say it is given here like this, it doesn't matter in fact, then these B1 will be connected to coil side B, and then E again, A again. So B1 will commutate first A and then B and then A again, and it is cyclic. That is called as commutation process. Always these B1 brushes touches always the coil side under the N pole. Always collects electromotive forces under the N pole. Okay. So it makes rectification. Doğrultma. Rectification. So resultant waveform will be like this. Okay, gentlemen, take care. In today's armatures, generally there are 1, 2, 3, lots of slots carrying armature coils, let's say 36, 35, number of slots in rotor, let's say 36, and number of commutator brushes, let's say C, commutator brushes by C, excuse me, C, commutator segments, number of commutator segments, and then here are 36 commutator segments causing 36 commutation process in one rotation. Now, what does it mean? One rotation. Let's say number of poles are 2. So in such a configuration, electrical angle is equal to geometrical angle, you know, because electrical angles will be P times number of pole pair times geometrical angle. So it is identical. One turn is 360 degrees geometrically and electrically. So there are 36 slots in rotor, makes 10 degrees. That is the electrical angle between adjacent slots. Electrical angle. Whole turn was 360, and then there were 36 slots. The angle between those two is those slots is 10 degrees geometrically, and it is also equal to electrical angle between those two slots. That means electrical angle means electromotive force, let's say A, let's say B, here it is. The phase difference between EA and EB is electrical angle. Here's an electromotive force induced, here's another one. But there's a phase displacement between induced electromotive forces, and it is gamma electrical. Now, ladies and gentlemen, the angle is 10 degrees right now. Tata. Take care. Here is the first rectified voltage. Here is the second one after 10 degrees. Here is the third one. Here is the fourth one. Excuse me. It is difficult to draw. Fifth one. And you commutate the voltages in each 10 degrees. So, what is the result between the brushes? The result will be like this. Let me show it here. Each 10 degrees, there is a commutation. So it looks very clear. Delta V, which is ripple voltage after rectification or commutation will be very small, ladies and gentlemen, will be very small. And then Now you understand that the figure will be like this. Rectified voltage will be like this. It depends how you distribute B theta. So that is good. Having such a smooth voltages or B distribution here, not sinusoidal, is better, gives a better result in induced EMF, because otherwise here would be some much more ripple. Let's say the figure would be like this. Delta V ripple voltage will be larger, but not, because we design poles to produce such a B flux, B of theta. Here is smooth, so it will induce smooth voltages. And you commutate electromotive force in every 10 degrees, but as a result you will have much more smooth voltage. That's good. It is why we make a good design or such a design in DC motor. We want an electromotive force having very flat here. In fact, again, we want to have small harmonics, but the main purpose is having smooth electromotive force. So we use such a flux distribution, and then to have such a flux distribution, we use such a pole phase. Okay, let me show you again. In some drawings, I draw, here's a pole, let's say, and here's a pole, and then that's it. That is just a sketch. Just a sketch. I don't know how to spell. Just a sketch, just a drawing. And then, in fact, in real life, here's a pole, here's a pole face. Pole face. Pole face. And here's another pole face. Here are pole coils, electromagnets, and here's rotor. Here you see such a pole phase construction to have a proper B theta. That's it. That is the better one. Here you see pole phase, magnetic field lines, almost flat here. B theta is smooth here, and then decreases down to 0 here. Here are 4 poles, N pole, S pole, no pole, no pole, no pole, no pole, D axis, but quadrature axis. In a 4-pole machine, let's say here are 4 poles, N, S, and S. So D axis is the axis from N to S. That is D axis, not a curved axis from N to S. That is D axis. And here is the quadrature axis. Quadrature axis. Quadrature. Between the poles, there is no magnetic pole. that is quadrature axis, or magnetically neutral axis. Neutral axis, pole axis, pole or magnetic axis, that is magnetically neutral axis or quadrature axis. Quadrature means perpendicular to D. Yani dik eksen anlamına geliyor. Yani iş yapan eksene dik, quadrature. İkili işlerde kullanılıyor. Bir şeye quadrature olmak. Okay. I have introduced to you the waveform. Let's start today's special topic, which is electromotive force. Electromotive force in DC machine. Again, here are the notes you see. EMF and torque equations. I have downloaded this file. And here's a blank page. I arranged, I have cleaned the writings and I have added some more blank pages. And let me introduce you into induced electromotive force in DC armature winding. Okay, so far we have discussed that magnetic field lines will be like this from N to S pole, and then the distribution of B theta will be like this. It is almost flat, no change in flux density around the pole, but here it is zero. Here it is zero in the magnetically neutral axis. Okay, ladies and gentlemen, assume that there is a single wire conductor here moving towards the right. And what will happen? Here is a conductor. Let me change its color. Here is the conductor. And we apply a rotation to this conductor under such a magnetic field. What will happen? You should remember Faraday's speed law, speed EMF equation, which is E equals to BLV. Now, here's the length of conductor. Yes. Here's the velocity. Yes. That velocity is perpendicular to magnetic flux density. Yes, there is. Magnetic flux has some change under the pole. Yes. So due to that change, electromotive force will have some change. Okay. But finally, we rectify the voltage. Rectify the voltage because we want to induce electromotive force in DC. DC. We want DC voltage. So DC voltage is measured by its mean value, mean or average. DC means mean value or average. So between the brushes, let's say here's armature, let's say dynamo, here's the armature. Between the brushes, A1 terminal, A2 terminal, you want to induce a voltage. Let's say voltmeter, we use voltmeter to measure the voltage. You will induce such a voltage. But this guy measures average value. So when we say 12 volt DC, you mean always average value. When you say 12 volts AC, you always mean RMS value. RMS, root mean square, effective value. So in DC we use average value. No, now I want to calculate one of the EMFs of only a single wire, single conductor. EMF of single conductor. And it is the average value. It is the average value. But we generally use capital letters for average value or RMS value. So I will never mention again AVG, average. If I say capital E1 is equal to, let's say, 10 volts, you should know that that is an average value in DC. Average. If I say E1 is 10 volts in AC, you should remember that is RMS value in AC. Okay. Now, take care. I want to have average value. I wonder the average value induced in a single conductor. So, to have average value, let me calculate the average flux. Here it is, ladies and gentlemen. I can say here's such a B average, which is constant under a pole. It is a constant value, average value under a pole. I only discuss one pole because the induced, that is the minus B average. Okay. Here is the minus B average, but we only evaluate average value under each pole. The average value under this pole, average value under this pole. Minus B average. Okay, what is the B average? I don't know, but let's define. One of the EMF induced in one conductor in average value will be equal to B average times L times voltage. B velocity. Velocity, not voltage. Velocity. What is the B average? B average. Let me make much more definition. Here is the cross section. Here's the segment of circumference. Here's the length of the conductor or pole. Let me draw it here. There is such a pole face. Pole, area, pole. Area, pole, length. And what's this? In fact, it is here. Radius is here. Because we induce electromotive force in these contour or path. Okay, that is the radius. That is the segment of circumference, which is 2 pi r over number of poles. That is the segment of circumference. That is the length. So area pole is equal to pi r over number of pole pair. Those two will be eliminated. Times length of the pole. Okay. That is the area. Remember B. B is equal to flux over cross-section area. Now, ladies and gentlemen, assume that here are much more flux lines. It is very difficult to count up 1, 2, 3, 4, blah, blah, 10,000, 20,000, 30,000. Here are lots of flux lines. Okay, lots of flux lines. Let's say pole flux. That is the pole flux. All the fluxes coming out of one pole. That is all the flux coming from a pole going through rotor. Okay, that is the area pole. That is the average flux density. Okay, now pole flux over cross-section area of pole makes average flux density, and let me substitute it here, and then let's calculate V. V is equal to W times R. That is tangential speed, which is velocity. That is angular speed in terms of radians per second, you know. That is meter per second. That is the radius of armature slot. Here is the radius. Armature is rotor or armature. That is the radius. Average radius of any slot. Here are conductors. Average radius. Okay. Now, here we have two different parameters already defined. One is B average, the other is velocity. Let's substitute those two into the equation. E1, one of the conductor electromotive force, mean electromotive force or average electromotive force induced only in one conductor is B average. Instead of B average, I write flux over cross-section area. Cross-section area is here, pi r L and number of pole pairs times L here, and then here's the velocity, and then let's define WR, angular speed times radius of the armature. And here you see radius will be eliminated, length of the conductor will be eliminated. So resultant electromotive force across one conductor as a mean value is flux W and P over pi. Looks like this. Okay. That is the average or mean EMF of one conductor, one armature conductor. Now, gentlemen, what is happening here in the armature? In the armature, there are how many conductors? How many conductors are there in one path of armature winding? How many conductors are there in only one path of the armature winding? Only one path of the armature winding. What I mean, here are some brushes, let's say plus and minus, or A1 and A2 terminals. Between those two brushes or terminals, let's say here's the machine. Let me draw it again. Okay, here's the dynamo. Let's say dynamo. Here are the brushes, and here are the terminal labels, A1 and A2. And then inside the machine, here would be, let's say, 4 brushes. Plus, plus, minus, minus. Here are 4 brushes connected, and then A1 is here, A2 is here. And then between those 4 brushes, here are 4 current paths. Here would be 4 current paths. And now, here you see, you wonder, what is the EMF of armature between the armature terminals? Ta-ta! In case here are n turns totally, each parallel path carry n over double A turns. Here n over double A, blah blah blah. Let's say here are 4 poles, for example, and lap winding, so double A is 4. 1/4 of the number of turns in parallel path, another 1/4 of parallel path. All those induces voltages, and then all those voltages will be parallel, since you see the parallel paths. So induced EMF in one parallel line or path is important. That is the number of turns in one path. Number of turns in one path. But, gentlemen, we have made some calculations only for conductor, not for turn. Houston, that is one turn having 2 conductors. 2 conductors. Remember, I always said that those are active conductors inducing electromotive force, and those are end connections, connecting induced electromotive force to each other, and connections. So number of conductors are generally given by Z number of conductors will be equal to double of number of turns. Okay, what is the number of conductors in one parallel path? It is here. Number of turns in one path. Number of turns in one path times 2 makes Z one path. So it can be written as Z one path is equal to 2 times and one path. Beep, beep. And one path. It is here. That is the total N divided by number of total parallel paths. Total number of conductors divided by total number of parallel paths. So as a result, those two are eliminated. Number of conductors in one path, one parallel path, is equal to number of conductors, total number of conductors, over pair of parallel paths. A is number of pair number of parallel path pairs. Parallel path pairs. Just like 2p, that is the number of poles, that is the number of pole pairs, that is the total number of parallel paths, that is the pair of parallel paths, number of pair of parallel paths. Okay, how can we summarize the total EMF? Let's write total EMF. Total EMF E is equal to Z1 path times E1. E is equal to Z1 Mamma mia. I was right, but I got one more step further, so those parts are not necessary. Let me write down here. Okay, I will summarize what I have done. P over pi phi W. P over pi phi W. Now, it looks like mistake, but phi is equal to pole flux. I use this one. In some books, it is given as pole pair. Some books, it is called as maximum flux lines, since we have collected all the fluxes. But I prefer just flux, pole flux. Okay, here I have copied. Now, I wonder what the number of conductors in only one path. So, let me summarize it in a more clean way. Z1 path is equal to Z total over double A. Z over double A. I go a little bit further. N is not necessary. I made a mistake. No point. There's nothing wrong, but the standard EMF equation is in terms of Z, not N. I will show you. N is not used in standard EMF equation. So these parts are not necessary. The necessary part is here. Necessary. Okay, let me make an arrangement. E is equal to Z over 2 pi A. Here's the pi. And then flux. And then speed. And that is the total EMF. Total EMF. So then we call armature EMF. Armature EMF. Between the branches. When there is no load. No load conditions. I will introduce you. Now, here you see is a coefficient. When you manufacture a machine, Z is constant. When you wind up the machine, Z is constant. And then 2 pi A, again constant. So this coefficient is called as Ka, armature coefficient. And Ka is equal to Z over 2 pi A. Let me check it out if I am wrong. I can't memorize. Yes, here is something missed. Pole pair number. Yes, pole pair number must be here. This guy. So here's pole pair number. Okay. That is the armature coefficient. Now, finally, we have find out armature EMF between brushes in terms of average values can be given as a coefficient, pole flux, and angular speed of the shaft. Houston, that is the resultant equation. You should know. You should know. When you rotate armature, you induce this. Okay. Let's continue with torque equation. Let me make an additional explanation. In some books, armature EMF Ka times flux times angular speed. That is the most common one in American or British literature. But in some German or Russian literature, there is some other equation. Armature EMF is equal to Ke flux, the same one, and a new one, which is speed. That is radians per second, angular speed, that is just speed, revolution per minute. You also know, and there's a relation, you know, angular speed is equal to 2 pi n over 60. So let's rewrite this equation here. Ka times flux times 2 pi n 60. So Ka 2 pi over 60 flux speed EMF, ladies and gentlemen, here you see n to n, flux to flux. So coefficient EMF coefficient is this. EMF coefficient in Russian or European German texts is equal to 2 pi over 60 times armature coefficient given in American books. I prefer this guy, Ka. And then remember Ka was Zp over 2 pi A. Let me show you again. Zp over 2 pi A. And then here are 2 pi's over 60. And some of the terms will be eliminated. So resultant Ke is equal to Zp over 60A. You know, that is the number of pole pairs, that's the number of parallel pots in the armature, and Z is the total number of armature conductors. That is the number of parallel pot pairs. That is the number of parallel. And that is the number of pole pairs. You know, that is the key. All those are have the similar meanings because that is a coefficient. That is a coefficient and constant after manufacturing process. That is related with RPM speed. That is related with angular speed. That is the relation between those two. So just a different expression. And I have given the relations. Ke is equal to Zp over 60A, or Ke is equal to 2 pi over 60 times Ke. It is already given here. Okay. I recommend you to know the first one. I prefer this one. I later explain why I prefer this one. That is more scientific. Okay. Let's continue on torque equation, but we have limited time, I know, but it takes not too much time. Torque equation is a little bit easier. There are two different approaches to have torque equation. First of all, let me use the first long explanation approach. Now, assume that here's a conductor carrying some current. Let's say into the screen. There's a conductor moving into the screen. Ladies and gentlemen, what you see, please take care my camera. I apply right hand rule, right hand three finger rule. Let me change the direction. Here's the conductor out of the screen. There's a current I. The direction is out of the screen. Now, ladies and gentlemen, here's M pole, here's S pole. Magnetic field lines by your mid finger coming from M pole to S pole. Then, index finger represents the current direction. From camera, please take care. That's the current direction. And Finally, you have find out the direction of the force. Right hand rule. That is the force direction. Force. Force is equal to Newtonian force or Lorentz force. Lorentz force equation BIL. You remember this equation from previous courses. And then you know if there's such a event under the magnetic field, if there's a current carrying conductor, there's a Newtonian force due to Lorentz force. There's a magnetic field? Yes. There's a conductor having a length of L? Yes. There's a current? Yes, someone supplied. Okay. As a result, there's a Newtonian force. That force, together with the radius, result in a torque in one conductor. Armature torque of one conductor. Okay. This torque will be changed with assume that here's a b theta. So as a result of b theta, you know there was a b theta. B was changing like this, and the forces will be rectified or commutated by using commutator brush mechanism. So it is rectified. This part will be rectified somewhere here. But the force will be as a function of theta. Houston, it causes some vibration due to as a function of theta. It causes some noise, yes, and we don't want noise and vibration in the motor. It's a kind of distortion or disturbance. Okay, first of all, you should keep b theta as flat as possible in the waveform, and then you make some commutations as short as possible. Yes, we already designed electrical machines in such a manner. So let's think about the final result. In torque expression, again, we always use average torque. So torque average of one conductor, torque average one conductor of armature, I will call torque armature 1, is equal to B average IL, only one conductor, here it is 1, and radius, here it is. Here it is somewhere here. Let me define. TA1 is equal to force average times radius. Force average times radius result in average torque of only one conductor. Okay, we know the average B, which is number of flux lines around the pole over cross section of pole, which is 2 pi r L over 2 pi p and here's P pole, and then let me substitute T average here. Let me say only T1 for one conductor, and substitute B average, which is P pole times P, here it is, over pi RL, and then Houston, here's current of one conductor, and then length of one conductor under the magnetic field, and radius of the conductor's position. Houston, R will be eliminated, L will be eliminated. So resultant average torque for one conductor is pole pair number over pi, and then continue flux, then I will say only flux, then current, TA for one conductor, P over pi times flux times current of one conductor. Now, ladies and gentlemen, how many conductors are there in armature? In armature, there are Z conductors totally. So, total induced torque in armature is equal to Z times total torque average induced in only one conductor. That is the final total induced torque equation. Okay, that's it. But here's something more. Take care. Here are brushes. Between the brushes there are parallel paths. That current is armature current, called as, here's let's say motor. Here are brushes. That is armature. The terminals A1 and A2. Here you see the current. Let me change color. Here you see armature current. But small letter I is conductor current. What is the relation? Here you see conductor, current carrying paths. So small I is equal to total current over number of parallel paths. Houston, that is important. That is why I lectured some information about the windings. Number of parallel paths was in EMF equation. Somewhere here, 2 pi I, you see in EMF equation. And number of parallel paths are again here. So let's substitute Z times number of pole pairs over pi, Houston times flux, and substitute current. Current is here. Armature current over double A. Let's make a new arrangement. ZP over 2 pi A. I have collected all the constants in the beginning, and then flux, and then that is the pole flux, you know, and then armature current. That is the induced torque. induced average torque in armature. Induced torque value equation in armature. Now, ladies and gentlemen, what you see? This guy. Take care. Houston. It is here. ZP over 2 pi A. ZP over 2 pi A. It is already defined as Ka. So induced average torque in armature is equal to Ka times flux times armature current. Houston, that is the induced torque equation. And here was the induced EMF equation. Here it is. And then we are about to get in end. Equivalent circuit. Now, gentlemen, we have armature EMF. Ka times flux times angular speed. We have torque equation. Ka times flux times current of armature. We have such a design, let's say dynamo, that represents armature, symbol of armature. Generally, it also represents DC machine, symbols of DC machine. Now it is written as dynamo. It would be written as motor or generator. It doesn't matter. Sometimes we say generator, sometimes we say dynamo. Dynamo is the nickname for DC generator. Now, where is EMF? Houston? I don't know. You know. We have already mentioned that EMF will be induced in one parallel path, and here are multiple EMFs connected in parallel. Where is EMF? Ta-ta. EMF is between brushes. Let's say here's one brush, A1, let's say terminal. Let's say here's the second brush. EMF is across the brushes. EMF is induced in those conductors, connected in some manner in different parallel paths. There are different brushes, different number of brushes connected to each other, and then we see EMF. Okay, here are the terminals A1 and A2. Here's a magnetic field. Let me say here would be a winding, something like that, or something like that. All those are represents winding. But if those are windings. But if you draw such a figure here, it represents permanent magnets. Now, if you say dynamo, blah, blah, here's something like that. That is the representation symbol of permanent magnet DC generator. Dynamo. That is the symbol of DC generator. That represents, this part represents permanent magnet. Okay, gentlemen, that is the symbol. Take care. The symbol in this box. So, for example, if you draw dynamo, And then here's something like this. Beep. It is wrong. This guy must be here. They are together. It looks like this. Here's, let's say, a MOSFET, N-channel MOSFET. Okay. Instead of drawing like this, you draw like this, for example. Let's say, is this a MOSFET? Looks like MOSFET, but not. No one can draw like this. MOSFET is this. Here's a gate, drain, source and channel, source and gate. That is the N-channel MOSFET. So it is similar to MOSFET. The components must be together. Excitation coil, field coil must be next to armature. Okay, now what does it mean? Take care. Inside the armature, there's a independent voltage source, plus and minus. The value is armature EMF, mean value, DC value. And then there are some resistances. Yes, this is the resistance of armature coil. Here will be some inductance of armature coil. So that is the representation or equivalent circuit, of DC armature. Now, why I drove this in such a manner? Because that is dependent voltage source, dependent voltage source. EMF it depends on Ka, a coefficient. Magnetic flux coming from poles. Ta-da! Here it is fixed because of permanent magnets, but there will be electromagnets current controlled. Let's say here's a dynamo, here's a field coil, and here's a control rheostat, RFG. Here's the external battery, and then by changing these rheostat, you can control field current here, and then you can control field. Here's the armature. Ta-ta. When you rotate machine at the speed of omega, you can control EMF. PA, flux, W. Now, ladies and gentlemen, flux will be a function of field current due to electromagnets here, and then speed will be supplied by a prime mover. It depends the prime mover. Here will be a gasoline engine or diesel engine, it doesn't matter. So EMF will depend on flux or field current and speed of the shaft as well. Finally, I have introduced to you equivalent circuit of armature. But in steady state, LA looks like short circuit. Makes no change. We examine DC machines in steady state always in this course. So L is neglected.